Okay, we're gonna try that again. Welcome to ECS Day, Declaration Week. So you know who I am already. The first 45 minutes of this is the professor panel. So a lot of professors from the ECS department took a chunk of their time today to come and talk about their research, about themselves. Next 45 minutes, we split up. I'll let you know when the 45 minutes are up and we have other activities. But in the meantime, feel free to scan that QR code to enter into our raffle. And we'll start with Professor Datta, who's going to give a few opening remarks.
I'm guessing I'm on camera. Okay, good. Okay. Hello to the people let me try this. I don't know how we'll test if people can hear us. I don't know. Okay. No, I know you can hear me even without the microphone, but what about virtually? Okay. Okay. So welcome everybody, those of you in this room as well as remote. So my name is Suprakash. I'm the chair of EECS this year. I'll keep this very short. You'll hear from a lot of our colleagues about the diverse interests, the diverse work, the diverse subjects taught and worked on by EECS. So I met a bunch of you or your peers in September, and I'll repeat one thing I said, which is the good news is that we are a young, growing, vibrant department. The bad news is that we are a young, growing, vibrant department. So I'll elaborate a little bit on each and I'll hand it over to my colleagues. So we've grown at an astronomical rate. We as a department, in terms of students, in terms of faculty members, we've been doubling in undergraduate student population every 4 years. So over the last 8 or 9 years, we've grown by a factor of 4. So one thing that's resulted in is we've added about 18 new faculty members last year, mostly between July 22 to the last one joined in on January 1, 23. So the number of professors has grown from 62-ish to 81, about 80 or 81. So we are a huge department. You'll find a vast assortment of courses, research interests. So whether you're looking to learn certain things, whether you're looking to have research experience, project experience on certain things, you'll find huge number of projects and research interests in general. And you'll hear from half a dozen or more of my colleagues. The bad news, as I said, is also exactly that. Our growth has resulted in higher class sizes a little bit, and more importantly, just the trouble getting into our programs. We've become extremely competitive, both on the computer science side and on the engineering side. I'll mention, I know most of you are engineering students, or probably all of you, but we run 3 programs in computer science, computer security, and digital media, which is interdisciplinary with the Faculty of Fine Arts. And then on the engineering side, we run electrical engineering, computer engineering, and software engineering. So one department, 6 programs. Particularly on the engineering side, things have become very competitive in the last 2 or 3 years. Wasn't the case. Computer science was a much older program. It was competitive even. So please make your choices today thoughtfully. These choices are important. And please don't be surprised that the process, unfortunately, is competitive. There's more seats, there's less seats, especially in computer and software engineering, than there are people interested. And we are working on different things to try and mitigate the pressure, but pressure is undeniably here. So unless there are other questions from people in this room, I'll stop and hand it over to my colleagues. Thank you very much.
All right. Thank you, Professor Datta. So Professor Srikanta is going to speak next on IEEE.
Hi, everyone. Can you hear me? Okay. Hi, everyone. So welcome to the Declaration Week. I didn't realize that the font size is so small, so I'll try to, summarize what's on the slide. So I'm here to talk to you about IEEE. Does anyone know what IEEE stands for? Have you heard of IEEE? Raise your hands. Okay. So anyone want to take a guess on what it stands for? What it's the expanded version of IEEE? Institute for Electrical and Electronics Engineers, IEEE. Okay, so it's a very it's a professional organization, and we have a York chapter that is currently not active, but we are activating it. It'll be in full, it'll be running in full speed soon. So we have planned a lot of activities for the York chapter. But to give you a summary of what it is, basically, why you want to be a part of the York chapter's IEEE student branch is because you want to be technically current, and if you want to be, if you're interested in continuing education after graduating, they offer a lot of courses. Also, there's a lot of career resources, professional networking opportunities with industry partners, and even on campus, we're running a lot of local events. And there are also recognitions like IEEE membership at the senior level or like various levels. And they also offer a lot of scholarships, funds, and discounts on various things. And they do a lot of humanitarian programs. So yes, there is a price tag. There's a membership fee per year, $36 per year for undergrads and grads. So the way you can participate is one, by taking executive roles to run the chapter. So you can gain experience in leadership, web development and in event management, or you can participate in these events that we are planning. So we plan some examples include hackathons with companies, technical interview nights with alumni or your peers, workshops on programming and electrical engineering concepts, summer research information sessions, industry nights, and tours of various companies and facilities. So if you're interested, please join. Hopefully, Luca will be sharing the slides at the end, and you can see the link here to join. Yes, that's it. So if you have any questions, let me know. Anyone have any questions? Yeah. So I'm actually hoping that we'll be starting by this by February-March timeframe, and hopefully we'll have a couple of events every year in terms of workshops or information sessions or practice interview sessions. So very soon, hopefully, but I cannot tell you the exact timeline because we are sorting that out right now. How is it different from Lassonde Engineering Society? That might be a question you might have. Maybe we have more focus on EE, electrical engineering and electronics, which has a couple of society. So we have a couple of subdivisions in there. Like you can take a look at the website. There is Signal Processing Society, vehicular technologies, power engineering. So there are different branches within IEEE that might be of specific interest to you. And okay, so thank you all, and I'll pass it to Luca.
Okay, so up next, Professor Jackie Wang is going to speak about his research and speak about his classes.
So I teach many courses in the EECS department. So I used to be a student in the same department back in 2006, a long time ago. It's a pleasure to actually come back to my home department and also teach many courses again. So what I would like to do is, before I'll try to maybe put all my courses together. They are the core courses you will have to study if you actually declare to be CS or software engineering students. But for now, let me put you in perspective. Let's imagine if you chose the major and when you graduated, what's going to happen? Okay. So I'm not sure if you heard about professional engineers, especially PEO. Anybody heard about PEO before? So it's Professional Engineers Ontario. Very good. So basically, if you want to work in, for example, safety industry, it's a requirement for you to be licensed. Even in Lassonde, for me to teach you guys, for me to be qualified, I need to be licensed as well. So that's kind of the professional license we're talking about. I want to quote some sentences from there. Don't worry, it's not going to be very long. It's very dry. I just want to point out to you some highlights. If you ever want to become a professional engineer, what kind of criteria you need to satisfy? So they have the so-called code of ethics, meaning that you have to conduct your profession with certain principles. They mentioned that you need to be fair, you need to be loyal, you need to be dedicated to the public, and also you need to be having high ideals. So these are kind of the practices beyond the courses you will learn. But I want to talk about something more relevant. You want to be knowledgeable and you want to be competent. So these are things you will actually learn in the EECS courses, which I'll give you some roadmap about. And what will be the consequence of misconduct? Given that you're so competent, at the same time, you're taking so many responsibilities. So if you really fail to meet those responsibilities, either if you're lucky, you just get your license suspended or terminated, or you might just get a lawsuit. Let's say you're hired to build some bridge as an engineer, and somehow the bridge, let's say, crashes. Let's say 5 years later. In that case, you'll be held responsible. You may have to go to jail. So I want to restrict the domain to just the safety critical domain. So that's really the thing I have been trying to train my students with. Whenever you're building some system, think about should be of the highest standard. So by definition, a safety critical system is really a system where the failure can cause to be death or serious injury to people, or could be lose a lot of damage to some equipment or property, or it could be some harm to the environment. That's just the definition. Let me pause a bit. Based on this definition, can you think of any systems you know of that's safety critical? Absolutely. You mentioned two. Let me write them down. Aircraft, for sure. Aviation domain. And also nuclear. And I'm not sure if you know about the Darlington shutdown system. You know, in Ontario, actually, we use a nuclear power plant. So there are two safety shutdown systems to make sure if there's anything wrong with a nuclear reactor, they're going to shut it down right away, so we don't have any harm. Luckily, the engineers who build the two shutdown system, they are very professional, so we don't have any issues so far. So definitely nuclear. Anything else? Any other system you can think of? Let me mention one. How about pacemaker? Have you guys heard about pacemaker before, right? So if you want to install maybe some pacemaker into your heart to make sure help you the heartbeat. And another one which I teach in my course, which I'll mention, is about bridge controller. And that one is obvious. You want to make sure if you are trying to build a bridge, number one, it doesn't collapse. And if there's a one-way bridge, there's no collision between the cars. But how can you be so sure it is the case? You will really rely on some underlying rigorous analysis based on math. All right, so that's about the perspective I want to put you into. So if you really chose the CS or SE major, so that might be a career path you would like to pursue, to kind of become a professional engineer and build something that our life depends on. So let me go over with you about the courses I have been teaching, quite many. I have been teaching, for example, I know you guys just took 1011, the MATLAB course. So it's more like a sequel to them, to it, 1021. And also 1022. So these are the courses for object-oriented programming, which is a very different paradigm from what you learn as a MATLAB. So MATLAB really tends to be a little bit more sequential. OOP is a little bit different way to think about stuff. I might just be able to give you some example a little bit later. I taught these two, so that'll be for your first year, the second semester. And also for 2030, so that'll be the advanced OOP. We talk more advanced subject like inheritance, and maybe aggregation, composition, and etc. And also 2011 will be the course that you will definitely need if you want to maybe go for some job interview when they ask you some coding problems. So that'll be 2011. So far we talk about, what you can think about, you definitely take these two, either one of these. If you're CS, you take this. If you're engineering, you take this. And then after that, you take 2030, and then you take 2011. That's really what we call the programming courses sequence that will build a foundation out of you. After that, there are two ways you can go. Of course, you can go both if you want to. Either you're more interested in the system development in the practical aspect. In that way, you can definitely take the 3311, the software design course, where you're trying to build some very substantial projects with many, many functions and many, many modules. And you want to see how you can organize the module in a way that really makes the most sense for maintenance and also for working. And also we got 4302. So this course, excuse me, this course is a bit special. It's called Compilers and Interpreters. It's currently more like a CS course. I'll just mention that in case you're interested. So this would be what I consider as a final course to really synthesize all your programming and design abilities into one, because you can really build your own language. If you think Java is not cool enough, if you think MATLAB has many deficiency in terms of the feature, you can definitely design and also implement a language yourself and implement a tool. And you can translate from that language to anything else. So that's really what the compiler course was doing. We actually had some very exciting projects that my students have been doing for the last two iterations. So that'll be one path. And the other path will be more mathematical. If you really enjoy math, then you can take these two courses, 3342. So that's for system specification and refinements. And also 4315, safety critical system. These two courses also teach you how you can really use the math, like a predicates and propositions, to model the system and try to verify them with respect to certain properties. That's basically what these two do. So that's more like what I have been teaching. You may not necessarily meet me in the course, but these are what you will learn as a software engineering major, a CS major. If I really ask me which course you must take, this one. I might have some type of example, maybe. One example. Let me do one example. I'll give you guys a choice. How about that? I have one example for this course. I have another example for this course. This one will be more like an introductory OOP. This one will be more like a data structure. You guys have any preference? Data structure? Okay. I thought you would say that. Okay. How about this? Okay, this is a problem. Let me give you the context quickly. The problem is like this. Let's say we are trying to create a database with for a mega city. Let's say we got 10 million people of record to store. So 10 to the power of 7. So that's 10 million. We got this many records. And let's say we use something you know already from 1011. You know what a sequence or what an array is. Right? Let's say this is what we have. We have a database, a single array, let's say a very, very long array. And then let's say indices start with 0 and all the way to 10 million minus 1, a very long array. What we really want to do is to really have a very efficient way to locate a person's record. Let's say if I give you my social interest number, the SIM card, which is unique for everybody, that way I should be able to fast locate where my record is in the database. Let's look at this particular syntax very quickly, and then we can do a little bit discussion, and then we're done. This is written in the Java syntax, which you will learn in 1021, also 2030. Also 2030. Let's go over that very quickly, and I'll ask your opinion. Given some input, SIM card, what I will do is I'm going to iterate through this long array, starting from index 0. Every time I want to make a progress, I want to increment the index by 1, meaning that I want to look at index 0 if the current index contains a SIM number that's matching what I'm looking for. In that case, I return this one here. If it doesn't, I go to the next index 1 to see if they match. If no, go to the next one. If no, go to the next one, and etc. Okay, that's my proposed implementation for now. In 2011, what you will typically do is when you are presented with a solution, you want to know, number one, if it works. That I can tell you it works. Number two, is it the most efficient way possible? Any comments you want to say before I give you the solution? Yes. It will take a long time. Can you be a little bit more precise? Yes. Let me try to rephrase that a little bit. Absolutely. So the worst case would be, let's say the record that we are looking for happens to be here. So if we start from the beginning, we want to go all the way to over here. So that means we need 10 million iterations. Yes. Okay. If you want to break it into half, that's true. Well, if you want to, are you thinking more about binary search? Okay, if you do binary search, it's an implicit assumption the array is sorted. But we don't have that assumption. So breaking it in half wouldn't help. Right, so this is not very efficient because in the worst case, you may have to scan through the entire array to really find out where the record is. So what you will learn in 2011 is a very foundational data structure. I'll write it down and I'll explain it briefly and then I'm done. It's called a balanced binary search tree. A tree looks like this. Rather than like an array, you always go to a single successor. It's more like a nonlinear structure, like a tree over here. Okay? It's more like a tree. Okay? And what's really a binary tree? That means every node has 2 successors. And what's really a search tree? A search tree simply means it's actually, you want to satisfy a certain property for you to really search for the record. Let's say if I have a node over here, and then I have 2 subtrees over here, I want to make sure everything here is less than, everything here is greater than. Don't worry too much about why. You will learn about why in 2011. I want to talk about this one more so I can make a conclusion. What about balanced? The balance here is the most critical property. The height of the tree over here, mathematically, is going to guarantee it will be log base 2 of the number of records you store in the database. Okay, why? That's something you will learn in the 2011. But in order to really make the search work, each time you will only go to the left or you go to the right. So if you only go to the left or go to the right, rather than going both, it's guaranteed you will only go for log n times for the iteration, rather than just n times. So now, final math question for you. What would be log 2 and then 10 million? It wouldn't be just 10 million anymore, right? Like in the worst case. It turns out it's only about 24 on the math. So by using a balanced binary search tree, you only need 24 iterations to really get to the record, as opposed to 10 million. That's kind of the efficient data structure we'll teach you in 2011. You need to know how to analyze, also you need to know how to solve it. Anyway, I hope it kind of motivate you for some courses, but if you got any questions, you can also search me, Lasong, and then look at my lectures. I post all my lectures online. Okay? Thank you. Okay, just in case. Of course, absolutely. Thank you so much.
All right. Thank you, Professor Wang. Up next, we have Professor Fokafis.
Hello, everyone. Thank you for having me, and welcome to Lassonde, even with a few months delay. So my name is Marius Fokaevs. I am a semi-new professor at the EECS department. Because I also started work about 7 years ago. So my expertise, if I want to put it in layman's terms, change management for digital systems. So I am a software engineer by principle. I don't know if I am privileged or unprivileged ones, but I apparently have a good pool of students to pick from. So a little bit about me. I hold a Bachelor in Science from the University of Macedonia in Greece. Software engineering. As I said, I was a postdoc fellow for about 2.5 years here at York, working with at the department. I held the position of assistant professor in the Department of Computer and Software Engineering at Montreal for about 5 years before I joined back at York this summer. I have been doing a little bit of a teaching over the past 5 years. So here in the department and before that in Montreal, I was teaching software design and architecture, all 3311. In that course and in general in my teaching around software design, I'm focusing more on distributed software architectures, problems around software evolution and maintenance, software design, software quality, service-oriented applications and architectures, cloud computing, and software architectures for big data. So this is also the topics I'm mentioning here are also part of my research, which I will give you a bit of an overview. I have also been teaching software quality. Now this term here at York, this course has transformed for me mobile user interfaces. It's a little bit of a more specialized course, but I'm still teaching some of the principles around software quality and software quality assurance processes. We're looking into quality standards and metrics, some testing, and I do have an expertise, and I'm putting that expertise in my classes around software performance, performance modeling, and capacity planning. You have heard, has anybody heard or used like Amazon Cloud, Azure, Google Cloud? You must have heard the term auto-scaling, right? Or at least read it in some kind of documentation. This is when we are able to commission resources, additional cloud resources, when our application needs it, right? So I'm working on the theory and practice of this topic, how to do scaling based on the performance of our application. And I'm also doing a little bit of software security. I have a little bit of teaching in software security and a little bit of research on that topic. So the thing is, I want to grab by this slide and give you like a couple of sentences to motivate you about software engineering. I understand that in your mind, software engineering may not be what you would consider the traditional type an engineering discipline, right? The main reason is because software engineering doesn't always handle tangible things, okay? We do not build bridges, we do not build buildings, we are not experimenting with real equipment, not all the time, okay? We do have some hardware that we can play with, okay? But what makes software engineering an engineering discipline, not just, science, is exactly what's happening before and after coding, which is the design and the quality. As engineers, you are responsible of providing solid design based on proper disciplines for whatever you're building in the middle, okay? And you're also responsible, as being said, as professional engineers, you're also responsible about the after of whatever you build, okay? Is this going to be working at the same standards after a month, after 5 years, after the end of life, okay? So you're responsible for the before and after, and this is what makes you engineers. There are also ethics and responsibilities in software engineering as well. So I can give you some scary examples about medical equipment or airplanes that had really bad stories behind them because of software, okay? So do not think that this is a lesser engineering discipline just because of field tangible. So I will give you a couple of, I have to mention there is a second part in my teaching. I'm actually a faculty bound for the Markham campus. I don't know if you've heard that York will have a Markham campus. So Markham campus is built with some new programs in mind. One of them is called Digital Technologies Program. Both of them are very innovative programs. So DT is having a philosophy of experiential learning, work integrated learning, meaning that the students are going to be attending classes in parallel with their jobs in a tech company or in a tech related company. So the teaching works like the student comes in for a couple of weeks over the term to get some contact with the teaching stuff, and then they go to work, and the assignment is, this is what you have done that is related to the course. Let's discuss it from the perspective of the course. Let's say that you're writing some code for a social media company. We're going to come back and see, for example, what is the design of the code you're writing? What is the quality of the code you're designing? And this way, you're learning based on what you're doing in the company you're working at. From my perspective, there are courses about software engineering practices, communication and collaboration in the work environment, work ethics, and other related courses. The second program is computer science for software development. This is to say software engineering. I will be responsible for the cloud computing stream. So this is, again, a specialized program for software developers and software engineers. But this is built with the flipped classroom model. So it's not like me right now speaking to you about theory, blah, 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 slides, boring, let's look what's happening in Instagram. You're actually going to be the ones that, you're going to presenting your projects, your assignments. I'm going to give you some readings, and then we're going to be discussing in groups. So it's more of an interactive model. Both of the programs are based on novel delivery and teaching methods. Hopefully, that's traditional. So in the cloud computing stream, there is also a data science stream and a software security, cybersecurity stream. Okay, so in the cloud computing stream, we're going to have courses like distributed and parallel computing, introduction to cloud computing, software development for cloud computing, DevOps, and SRE. SRE stands for Site Reliability. Term started in Google. Very, very, very recent novel things. These things are no older than 5. Okay, so we're talking about very topical, very current technologies used in. So a little bit about my research. My main question is how to manage changes in digital systems. And I'm not talking just about software, but any kind of digital system. Could be banking system, could be a health system, whatever that is written with software. Why is software change challenging? Because everything is running. You have online systems. So what happens when a change happens or needs to happen and we don't want to interrupt things? You've heard about Twitter going down for 2 hours, Instagram for 5 hours. How do we avoid these things? Well, we have to make something change. How do we manage changes in heterogeneous and distributed environments? How do we not affect our clients? What happens if something else changes that affects our system? How do we deal with this change? How do we manage trade-offs between quality, cost, and revenue? For example, I mentioned scaling before. Do I add unlimited resources to maintain the quality of my application? Probably not. I will not have a budget for anything else. I have to make these kind of decisions. Provide the capability for continuous change management. This is what DevOps is in a sentence. Provide the capability to maintain availability under constraint. This is what the SRE principle is. Provide the capability for just-in-time dynamic adaptation. While I was at York as a postdoc, I was working with self-adaptive systems. As first-year engineers, have you looked into control systems, control theory, PID controllers? This is exactly what self-adaptive systems are trying to do. Okay, control the software system. Here are a couple of projects I have worked with my students. We have built an intelligent and autonomic management system for blockchain in NFT marketplaces. an economics-driven self-adaptive resource manager for industrial data science applications. We're working with financial companies to do that. And an energy-aware smart deployer of analytics on the edge for Internet of Things applications. This is our chance to play with something that is not software. Yeah, I have some current projects. You can look me up online. The reason I'm mentioning current projects, there are collaborations with IBM, with colleagues from epidemiology. I have, for example, a project where we're trying to provide a model-driven software platform to model epidemiological models like COVID-19, HIV, with climate models, to combine them with climate models to facilitate health scientists and environmental scientists in these topics. I'm mentioning this, so I hope I motivated you a little bit about the software engineering part. But if you're interested about research or about contributing to a research project, you can contact me. Lassonde has programs for undergraduate students to work with research groups here in the department. So if you're interested, you can. I would be happy to answer if you have any questions. I hope it was clear, not too boring. Thank you very much.
All right, thank you, Professor. Up next, we have Professor Bourgeon, who will be speaking about her courses and research.
Can you hear me well? I'm a professor in theoretical computer science, and I've been hearing about engineering, about like the doing of things. I'm a professor on the basics of things. Where do we stand on? Like, what's our ground? And this is in computer science. You will be taking some of these courses if you're doing software engineering, or you will be able to take some of these courses if you're doing software engineering, but it's mainly for computer science. The idea is we find where the boundaries are, because it's all nice and well to like think outside the box with things. What I try to teach is where is the box, and what are the things that can be done, and what are the things that cannot be done, and why. And this matters because, like, if you're trying to improve a system, you want to know how much margin there is for improvement there. And you know, that's not to say that everybody should be completely aware of this, but somebody should be aware of what's the margin of error. Somebody should be putting like the parameters and the limits, so that we all get a little bit of a better understanding on what we are dealing with. And if nothing else, this is something that you should take away from your studies. If you're studying any field related to computer science, you should know, if you're diving in on a project, you should have like the basics to find out whether something is possible and how much time you should expecting something to take, and like a computation or something like that. And this is more or less what we do. And how do we do it? Well, in the following courses. So first you have a course on, let's make everything here. What can computers do? So in the course 2001, Introduction to the Theory of Computation, the idea is to understand what are the capabilities of computers in general. Can we solve everything through computers? Does anybody have an idea? If I say, for example, I want to make a program that checks every other program and tells me if it's always going to stop. no matter the input. Can I actually do this? So like just raise hands if you think like this is something that would be doable. Like, I mean, we were talking about checking that systems work. We were talking about like security and in this software engineering aspect. Well, actually, mostly it's not really possible to have a program that for every single program it's going to check if it always stops. It's not possible. And this course is going to teach you why. And then you're going to understand how to find the boundaries. Well, if it's not possible, what is actually possible? Because maybe, you know, instead of trying to achieve the unachievable, the uncomputable stuff, you can achieve something else, and that's great. Then we talk about models of computation, because what is a computer anyway? So we have so many devices with so many different capabilities. And we program them mostly in similar ways. We have all these different programming languages, but what are the models that we base ourselves on to build all of these languages? So if I build a different computer with a different type of processor tomorrow, will it have different capabilities? Will it be able to suddenly solve this unsolvable problem that we just mentioned? And for that, it's important that we have good models that can be robust to change, because computer science is a field that changes very much. And these models include Turing machines. Have you heard of Turing machines? And automata, and there are many other models. And we are going to, in 2001, if you take computer science, you're going to learn about these models, and you're going to have some basics, some structure for understanding what is really possible to do with computers. Then, in third year, you have this course called design and analysis of algorithms. So now you know what computer is. You understand to a certain degree what the theoretical boundaries are for computers. But you've already been programming quite a lot. What makes an algorithm run fast? It's not only the hardware part. It's not only that I have a bigger, newer computer and makes an algorithm run fast. I have to have designed my algorithm to run fast. The Professor Wong, I think, told you about this like database search, and how instead of like searching one by one, I can do this binary tree search. Well, this course goes into the theoretical aspects of it. So if I receive one program versus the other program, it's not only because I understand how the program works that I know how fast it goes. I should be able to look at the code and have like a basic analysis. Imagine that I have an algorithm that solves something. I run the program, and the program is just not finishing. I should be able to look at the code and figure out, in theory, what should the code be doing and how long should it be taking to solve something. And this is what we do in analysis of algorithms. We learn about practical algorithms and general strategies that work most of the time for designing algorithms, and we learn how good they are or how bad they are in specific situations, so that we kind of can understand in more general terms what approaches are practical to be taking. And so we have in this area, we have sorting algorithms, we have divide and conquer algorithms, we have graph algorithms, many, many more. And finally, a personal favorite of mine, we have in fourth year computational complexity. And this is even more on the theory side. This asks about like the hard the hard-hitting questions. Why are some problems harder to solve than others? So for example, for the database example that you saw before, you imagine it's like, oh, like searching one by one is not the best you can do, but there's this binary tree. And what if I would ask, is this binary tree the best I can do? Like, raise your hand if you think this binary tree is really the best you can do. Or can you come up with a completely different idea that's going to take the searches from 24 to 12? Like, this sort of questions are important because maybe you are faced with a situation where your database suddenly, instead of having 10 million queries, it has 1,000 million queries. And then you need to take a hard look and say, either my database is too large, or I need to improve this. And you need to know where the boundaries are for that. And you know, in a practical situation, maybe you just have to figure things out. But in the theoretical aspect, we can ask ourselves, how much of this is predetermined? You know, if I can tell you, well, no matter how hard you look, you're not going to find a better way to do this, then you don't have to look for it. You can look somewhere else. You can figure out a completely different way to solve this issue. But unless you know that, you may spend a lot of time and resources trying to solve this. So, you know, the theoreticians, we go around, we try to figure things out before they become a problem. That's part of what we do. This is where we also learn about the big questions. So have you heard about P versus MP, the millennium problem? If you solve this one, they give you $1 million. But it's pretty hard because nobody has been able to solve it for more than 100 years now, something. It poses this question because it turns out that guaranteeing that there's no better algorithm to solve something is very hard. And for a lot of problems, the so-called, in this so-called NP class, we actually do not know of any algorithm that's better, but simultaneously we cannot guarantee that there is no algorithm better. We've been trying to solve this for 100 years. It still doesn't seem that we're going to solve it anytime soon. So there are big questions in computer science that are still open. It's a relatively new field, but simultaneously it isn't. And we are figuring things out as well. And then, well, if we have some open questions, one thing that we can do is classify problems to understand better, for example, what the class NP is. It's also very good to have many, many examples of problems that belong to it. And if you have a new problem and you are trying to figure out whether you can solve it faster or not, maybe you figure out, oh, this problem belongs to this class. So maybe I can go around and I'm not trying to solve this question by proxy of trying to solve another NP problem. So classifying problems is also very useful in the general sense, and we do complexity in many, many other ways. In the research, but like in this fourth-year course, you get a taste for what complexity means and why do we care about it. And ideally, if you really love the theory side of aspect of things, you get a little bit of an introduction on what theory of computer science cares about. And if you are more on the practical side of things, you get a feeling or an understanding on how this basics of the theory work, so that when you are faced with a problem like this, you can sometimes take a step back, go to the basics, take pen and paper a little bit, figure things out, and this can kind of show you aspects of the problem that you're trying to solve or you're trying to program that maybe you hadn't considered before. So I think this course is very interesting, even if you are on the practical, you are more interested on the practical aspects of it. And why does this matter? Well, it matters because what do I care in my research? Well, we care about what can computers do. This is related to the 2001 class. I published a paper 2 years ago, now 2 years ago because it's 2023, called From Finite Valued Non-Deterministic Transducers to Deterministic Two-Tape Automata. You see the automata here. They are the same automata, the same model that you will learn about in 2001. We are still figuring things, new things out about models of computation with my co-authors, because you don't have to do it all alone. What about analysis of algorithms? Well, on different types of algorithms, we work on the online simple knapsack, which is online algorithms are a different branch of algorithms, let's say a different aspect of algorithms, and we are analyzing those with also any collaboration. And why do we care about computation, or what do we do about computational complexity? Even though we aren't solving the millennium problem quite yet, maybe somebody will, we still care about classifying problems. We still care about putting boundaries and understanding what's possible and what's not possible for specific problems and how hard they are. So, for example, we published this paper called Lower Bounds for Conjunctive and Disjunctive Turing Kernel. Even though this title doesn't look anything like computational complexity, this paper cares very much about how hard it is to solve certain specific problems and putting boundaries. So I hope that if any of you is interested in mathematics in the practical way, or in computer science in the theoretical way, that I've gathered your interest here. And even if you're not interested in those things that I've brought to you a little bit of an understanding on why are those things important and why having this like theoretical basis may be something that you think about when you plan your study. So thank you very much.
All right, thank you, Professor. So, some of you may notice we are slightly over time. I'm just going to take the moment right now because we do have Burge 316 booked to say that if anybody's interested in doing the electrical engineering demo, please follow Ayub. He's wearing the Lassonde hat near the door, and he will take you to Burge 316. If you're interested in listening to Professor Wang speak on her research, and then Alex, the Amazon software engineer, speak on his experience, stay here. We will also be doing the raffle in a short amount of time. Oh, without further ado, Professor Wang.
Hey, hello. Okay. Okay. So thank you for being patient here. So my talk will be short, and this will be the last one. So hope you can enjoy it. So first, a brief introduction about myself. My name is Ping Wang. I'm an associate professor at EECS. And this is my email and the homepage. So my research mainly is in the wireless communication networking area with a special focus in radio resource management, allocation, network protocol design, performance analysis, and optimization. Actually, this is some research topic which I have been done for many years. So before I joined York in 2018, I worked at NTU Nanyang Technological University in Singapore for 10 years. So I've been in this area for quite a long time. But in recent years, my research focus is mainly focused on this integrating AI techniques into this communication area, which is quite emerging and exciting research area. And currently, I'm a tier 2 York researcher in this AI-empowered next generation communication network. So we all know for mobile communication, we all know, right, it evolves very quickly from the first generations to the current 5th generation, right? So the current 5G can provide us with a very high, capacity. So the data rate is up to 10 gigabit per second, which is 10 times increase from the 4G LTE system, right? And also it provides us with very low latency. Like the round trip delay is just 1 millisecond. And also it provides a massive connection to many, a lot of devices simultaneously. So it also facilitates many new applications like IoT applications. Okay, so with that powerful capabilities, so 5G currently actually is expanding from the mobile ecosystems to support many new industries. So I think this is something on news, many of you already know that, right? So it can support us to achieve the smart, the smart education system, smart manufacturing, a smart city, as well as many. It is expected that by 2035, so this 5G network can help us to create about the 13 trillion economic value. Okay, well, we know that in order to enable this 5G and beyond the future communication network, so we also face many challenges. And this is why, as a researcher, so we are trying to address those challenges. And there are some key research factors which enables this 5G communication system and the future, communication system. Among all of them, so I don't have time to explain. AI-empowered communication system is one of the important, components in this research area, and more and more important in the future. So the reason is because AI actually have the strength to help us to address many these challenges which may not be able to address with some traditional methodology. So we know nowadays dynamic and complex. So because of densities, anything. Okay, so it brings many challenges for us to traditional method as what we do before using traditional optimization method. So we have to model such system first before we can provide an optimal solution. But for those complex systems, actually it's very hard, even impossible to build a model. This is a main challenge for us. And although we can make many assumptions, solve give a good solution, optimal solution is also very difficult. very challenging. So the issues that we deal with usually to solve those problems. Okay. So this is some challenge we face now. So and with the traditional method, very difficult to deal with that. So with that, so that's the reason now looking for the new technology, which it's not all, but many of them. Because with the neural network, allow us to find a near optimal, right optimal solution. Near optimal with computational efficient way with
All right, thank you so much, Professor. So, up next we have a Amazon software engineer, Alex Alwyn, coming up to speak on software engineering, his software engineering experience. I want to say right now, if you are interested in doing our software activity in the sandbox, feel free to follow Great Love up to the sandbox. And we will still be doing our raffle for our 5 gift cards and 4 plaques. But without further ado, Alex.
No. Can you all hear me? Sure. Okay. Okay. Get my. Okay. Hey everybody. Just a quick question. How long is it going to? I like the last. Right? Okay. So I won't go. So I'm talking today about what it's like to work in today's software industry. So we'll start with who I am. My name's Alex. I graduated from 2012 with a bachelor's. Very pragmatic engineer. So full disclosure, I'm not a background, and through the course of the talk, I'm going to be talking about software engineering. A lot of what I'm talking about applies to a degree in computer science or software. That's just me. So how do we make software better for customers? That has meant a lot of different things. It might mean building your experience, or it might be hiring whole teams of engineers. At the end of the day, I'm enjoying creating technology to solve actual problems. So, quick question. Everybody here in first year? Does anybody have programming experience? What languages? Okay. That was Python. Okay, sure. JavaScript, like web apps and stuff like that? Well, you're software engineer, software developer, data scientist. Yeah? Okay, cool. So what do I do? What have I done? So this is my very quick CV. So after graduation, I spent some time building SQL banks on my banking platform. That was a mainframe Java application. So I did that for a few years. Then I moved into the cloud development team, and that was migrating stuff from mainframe architecture. Then I moved into leading teams and building products, like apps, websites for everything from online banking, mortgage enrolling for a checking account or a credit card, setting client preferences. And recently I've joined Amazon Web Services as a manager, so I lead an engineering. So very quickly, is everyone familiar with AWS? Has all heard that before? Okay. So cloud computing, very quickly, cloud computing. In a very simple definition, cloud computing, Amazon Web Services is a cloud computing company. Cloud computing just means running your code on someone else's. That's all it is, someone else's mainframe. So there's a few examples. Let's say you're a large media security company. You have customers all over the world, and you want to be able to send them 4K content really quickly without any lag. How would you do that? You really have two options. The first one is to buy a plot of land, rent bulldozers, make a building, buy mainframes, put them in the building, and run your own data center. And then you're going to repeat that process for every country where you have customers, right? You need your content host where your customers are. Other option is to rent someone else's computers who have already done that. That's what AWS is. Another example that's a little different. Let's say that you are a large movie production company and you make animated movies. You need to do some really high quality rendering. So you need to render the animation. And how are you going to do that? Well, one thing you could do is go around and buy all the graphics cards that you can get your hands on, stacks and stacks of graphics cards, scalp them after you're done with them. So there might be some profit there. But you're going to have to do that and set up your own infrastructure. Or you can rent someone else's graphics card. You're going to need them for a few weeks. So that's, again, where AWS comes in. So cloud computing services provide compute, storage, and networking infrastructure to other businesses. So that's what cloud computing is about. There's Google Cloud Platform, Amazon Web Services, Oracle has a cloud offering, IBM has a cloud offering. Large space. What do I actually do inside of AWS? What does my team do? So we build defensive systems to frustrate attackers and keep AWS customers' data safe. In that sentence, phishers, anybody who create data, steal data, or take over accounts. Who are our customers? So I mentioned a couple, but companies like Netflix, Pfizer, NASDAQ, US government, there's healthcare companies, GE. So we have a lot of sensitive information, a lot of high value customers that attackers are targeting. There's a lot of security teams at AWS. So what am I talking about? I'm not really talking about AWS. I would like to share some of the things I learned during my career working with software. I want to be very practical, very about what it means to work as an engineer, okay? And what I think. Sound good? Yes? Useful? Okay. So the first thing that I would strongly recommend you do while you're here and after you graduate is to stay current and to keep learning. Today is learning, I would hope. But the software industry changes really quickly. The technologies we were using years ago today are completely different. So this is one of the most important things that you can do in software engineering is continue to adapt to new technology. And one of the things that comes along with that in the same theme is that your identity isn't your tech stack or your toolchain. I've worked with engineers before who are knowledgeable about like the programming languages they like, or the frameworks they like, or the tool chains they use, and they're really going to approach every problem like it's a nail and they have a hammer. They're going to use the same technique no matter what. That's what they think is the best, for whatever reason. The most successful engineers that I've worked with are the ones who pick the right tool for the right job. So they're going to look at the problem in context, decide what the right language is, what the right framework is, what the right technology is, and choose. So some examples, just to drive home what I'm saying here. Here are some very typical arguments, I'll say, I've seen engineers get into. At the top, we have Angular, React, and Svelte. Those are 3 different web app frameworks. NPM and Yarn. Projects. Java versus Go, server-side languages. Node versus Spring, it's like Node using Express or some other kind of server-side framework, and Spring is a Java-based. Python versus actual good languages. So I don't know. I don't like Python. I like Python. So one other one, Vim versus literally any other IDE. Anyone here use Vim? Yeah? You people? Okay. So a very quick sidebar on Vim. Because I'm almost certain if you go into computer science, computer engineering, you're going to come across it. So this is Vim, and that is VS Code. Could be any picture. It doesn't matter what it is. Vim is a command line text editor. That means that you can run it in like a remote session, like an SSH session. If you're programming on like a mainframe, you don't have windowing, so you can visually see what's happening. You can launch Vim and still do things like have syntax highlighting and have a terminal to like build and compile and test and stuff. But if you ever, one caveat. So I hate Vim, but one of the best engineers that I've ever worked with, who right now is a staff engineer at Wealthsimple, loves Vim, and they're excellent at it. They have it. Like, I've never seen code they will die with Vim. That's where they live. But if you ever want to get a Vim user really excited, ask them about hotkey setup. How they did this like super perfect terminal, and it only took them hundreds of hours. So I would stay away from it. So speaking of evaluating different choices, the second thing I would strongly recommend, or what I know you'll be doing as a working engineer, is evaluating technology. So evaluating technology choices is an important skill, in particular in the cloud computing space. Most software engineers today, cloud computing, that's where a lot of software engineers are expected to both write the code and the infrastructure that runs the code. That's an important distinction. So let's say that you're making a website. You're going to write some HTML. Doesn't matter what the website is. JavaScript. So you have some interactive web app. Well, you're still going to have to figure out what server you will host that web app on. And when your web app gets popular, you have millions of customers, you're going to have to figure out some other things. What load balancer are you putting in front of that? Not breaking down your server when it becomes super popular. What caching solution are you going to use? You're not reading disk every time. That's way too slow to do in a production instance. What are you going to do about security? As in our so these are all decisions that are made by engineers, not just writing code. That's not really where the responsibility is. It's really about the full stack picture of building and deploying production. The expert. There's no one else on the team, I mean, the other engineers, but there aren't other roles who are making these decisions. How to work within constraints, how to consider different factors, make the right technology choice, how to actually get your code. Here here are some examples. We're not going to go through all these, but some examples of the factors that I'm talking about. So all of these are some examples of things that you would have to consider when you're making technology choice. So let's say that you were on a team building a new web app and wanted to know if you were going to use Angular as a front-end framework. Well, you might need to make trade-off decisions. Angular isn't the most performant there. It's run kind of slower when you compare it to something else. But maybe your team has a lot more object-oriented coding experience, so you're going to be faster at building Angular apps. Or maybe it has better documentation or community support, or tool chain, better integration. So as an engineer, you're going to have to consider these factors, make the right choice before you even start writing a line of code. So here's an example from my team last week. We're literally figuring this out now. So we have a system that we have a system with processes deployed globally. Data centers all over the world, and we have programs running. Those processes capture traffic, so things happening on the internet. And we pull information out of that. So we would call them signals in the security space. So we collect signals all over the world, and we all of that data with single system decisions. That those decisions are typically safe, or are they evidence of an attack? And then what do we do about them? So we have a single file that all of these signals are written into. A single system that reads from that file has to make decisions. That's kind of a hard problem. What you'll see in a situation like this is write logs. You have multiple processes running at hundreds of transactions per second, writing into a single file. They're going to overwrite. They're going to conflict. You're going to have a problem. So how do we solve this problem? We're going to have to make some trade-off decisions. So there's a lot of different techniques we can use. One thing that you can imagine doing is instead of using file, use a database. Have all these hundreds of processes write to a database. Your decision-making system reads the database. Databases are okay. They don't scale performance, but maybe they're very easy to set up. There. That's what's called an event listener, but a program that reads events as they come in, and then it will extract the information from them and stick them somewhere else, and you can pull that into the decision-making system. But in this scenario, we're constrained. That decision-making system is black box to us, meaning that we can't see inside of it, we can't affect it, we can't change it. It is what it is, and it only uses it. So what do we do? That. Use a queue. Write requests or messages into a long list, and then you can have another process that goes along that list. So that's pretty easy. Here's some queues. We have a lot of queues. We're not going to go through all these, but there are lots and lots and lots of options for different queuing technologies to use. So as an engineer, you realize there's a problem. You want to have this really, really high file, realize there's a solution, use a queue. Okay, well now you actually have to do it. You can't just say day is done, you have to go off and implement it, right? So you're going to have to look at these and make trade-offs around security, performance, around cost, around complexity, and so on. So you get it. So you're going to have to make these decisions using fundamentals, which so despite the fact that technology changes and implementations change, and get a lot more options in a platform like cloud computing, the core building blocks that we use to build high-quality dependable software don't really change. They sometimes change, but they don't really change that much. So they change pretty often, but there are still some things that stay the same. So I would say the change in the software industry is very rare that something you learned 5, 6, 7 years ago, you're still going to use the exact same way. I'll give you one quick example. So there's a way you'll almost certainly learn about this. Has anyone heard of something called cyclomatic complexity or big O notation? Cyclomatic complexity is a way of mathematically measuring the complexity of an algorithm. That was really important. If, say, you were writing like a sort function, and you write on Java, and you wanted to sort 10 million records alphabetically, you could do cyclomatic complexity calculation and figure out ahead of time, oh, it's going to take it this long, it's going to cost this much money. Like in cloud computing, you're not writing like a sort function, sticking on a mainframe and running it. There's more important measures of software cost, software quality. I'm not going to say you're never going to do it because it depends on what your role is, but it's pretty unusual. Relevant measure. You're going to use performance, that first one. You will still measure the performance of, say, cloud-based systems. You won't use cyclomatic. But the underpinning of we need to make sure our applications are performant still applies. And they're going to apply no matter what role you find yourself in. You could be working in cloud computing, you could be working on embedded systems. You're still going to do it. If you're working on medical devices, say, and you're working to build pacemakers, you still need good performance in a pacemaker. Because if it ticks late, like I'm not a doctor, that's going to be a problem. And if you're building some, super high availability streaming platform, you're going to want them both to be secure. Because I shouldn't be able to modify your pacemaker over Bluetooth, just like I shouldn't be able to hack your website and steal data out of it. So even though those are very vastly different software, the still apply, no matter what you're doing. So now for something very different. We've talked about staying current, understanding technology, learning fundamentals, communication. So communication is not technical, but I will say it's extremely important. Successful engineers work in teams across the board. I don't care. Every successful engineer I've ever met always worked in the team. Startup, they can be at an enterprise, it doesn't make a difference. 20 or 200 or 20,000, you will be in a team, you will be. So you're going to need this. You're going to need to be able to demonstrate value of your ideas and your proposals, get buy-in, and move forward in the way that you know is best based on your and all those decisions you're making as an engineer, whether they're how you chose to code a particular function, or whether you're selecting an architecture from the entire system, you need to be able to show your work, both to the other engineers and the other stakeholders who are impacted by that. Here's an example. So this is a pull request from GitHub. It doesn't really matter. It's just an example. There's nothing particularly interesting with that text. But it's from the Kubernetes GitHub. What I want to show here is how much detail goes into explaining. So this is a pull request. This is someone has gone off and made a code change. You can see this one line change here. I think there's more lines, but this line change here. They've added a new variable called context into that function. It doesn't really matter what it does, but it's expected that the person who submitted this code can clearly explain and demonstrate to the rest of the engineers of the team what this change is, what it does, how they tested it, and what the other impacts of this change might be. It happens here for the entire feature. This is them describing what I think this feature will be. And this is a conversation between 2, 3 engineers on this one single change. They have different opinions on whether this change should be made this way, in this place. And before this code can go anywhere, they need to talk about it through text to all get on the same page about the implications this change is going to have on the rest of the system. So it's not as easy as like the code speaks for itself. Like I wrote perfect code, submit it, you should just be able to read it. It doesn't work that way. So a quick sidebar on code reviews. You may not have gone through code reviews yet. I will tell you, you're going to do a lot of them as a professional engineer or a software developer. like the bread and butter of the job. It's best to assume the person on the other end of the review has good intentions. Text really sucks for communicating tone. Someone's reviewing your work. It can feel very uncomfortable. But it's a really important step to make sure the code actually works, that it's bug-free, that it's high quality, that it's meeting whatever metrics your team is expecting. So being good at code reviews, reading well in text, being praise is actually a really important skill. It'll help a lot. Totally different form of communication. Diagrams. Doesn't matter what the diagram is, it could be anything. This is an infrastructure diagram. So understanding and producing good, clear diagrams. When you're trying to discuss really complex concepts, being able to draw a design either on a whiteboard or on a computer with software is a really information-dense way to get across. Learning how to create well-structured diagrams and walk others through them is a really useful way to reason out the system when it hurts the system. When you're working in an industry job, you're not going to be building a single program. You're not going to have one isolated set of code. Certainly you won't. You're going to be working on very large distributed systems, all contributing. Kind of reason about that program, understand how it's moving. Diagrams are typically the only way you're going to be able to effectively do that. It's just too and evaluate when you're talking about very specific detailed changes. So there are a lot of diagrams. This is, like I said, an infrastructure diagram. There are sequence diagrams, system context diagrams, a whole slew of diagrams that we exposed to understanding how they work. Another point about communication is you're not going to just work with engineers. So I'm almost certain that no matter what job you get, what company you work with, you are going to work with people who aren't engineers. Stuff that you'll be doing won't just be engineering. And that stuff will also be very important. It's going to matter. You might be reviewing UX mockups with a designer, or you might be meeting customers, talking to them about their requirements, or someone from the business team talking to them about what it is they want you to build. Budget conversations or cost forecasting. You might say, I need a new server. It needs to run this code. It's going to cost us money. Explain what that means, what the implications are. You're going to work with product designers, product managers, business analysts, testers, customer service reps, all kinds of different roles that you interact with in any job that you get in the engineering field. And that well, you're going to have to be able to explain technical concepts to a non-technical audience. It could mean all those non-technical people you work with, but it could also be someone who just joined the team. It could be a new grad who joined the team, who's just less technical. It could be even someone at the same level of seniority or the same level of knowledge that's familiar with this particular part of the system as you are. So being able to explain technical concepts in a way that your audience understands and can actually rock and appreciate is incredibly important. So when you're writing papers or you're giving presentations or you're demoing projects, those are all good opportunities to practice communication to the audience because it's something you're going to be doing forever if you're working in the software industry. So I've made a lot of broad statements about how the software industry works and how but the reality is that the number of software engineers today is massive. The product is software, so often Google or Riot this kind of advantage is software. Someone like Amazon sell physical goods. It just happens to be online. There are thousands of other companies that use software in their businesses. Well, everything from like agricultural companies and healthcare. I don't think there's a field possibility. I don't think there's a field today that doesn't rely on software to operate part of their business. So quite simply, I don't know everything. There's just too many jobs and too many roles. I will say that everything I've shared with you so far is true in my experience. I don't know that it's universal. So I've never worked in low-level embedded systems. Hasn't been part of my career. If that's something you end up doing, you might have to use Vim. That's tragic, but need them. So I'd say a little bit. And similarly, there are a lot of jobs that aren't called software engineers or aren't called computer scientists, where having knowledge about how software is built is a valuable skill. Might not be explicitly writing code, but a role like a technical project manager or a technical or product owners or software architects or designers or analysts. Those are all jobs that require a background in software without being called software engineer. So it opens up a lot of doors. So we talked about a lot of things. In summary, here's what I'd have you walk away with. Stay current, learn how to evaluate technology, learn the fundamentals of building software because you're going to use them no matter what role you find yourself in and no matter what changes in the technology landscape. Communication is incredibly important. You can't sell your ideas and you can't talk to others about your ideas. Path forward, your ideas won't get bought into, and that software is everywhere. There's every field has software in it. There are a lot of jobs that may not be but so it's declaration week, yeah? That's why I'm here. I didn't have a declaration week at Mac, so I only loosely understand what that is. But everyone's picking a major. Is that the point? Okay. So what major should you actually pick? Probably doesn't matter. Probably doesn't matter to you. So I think it should matter a lot to you. Spending your time in school, challenging, walking away with a degree in a field that you found really interesting. Really, really, really interesting. That's incredibly important. But in my experience hiring engineers, I've never and moved on just because of the name of the degree. So if it's computer science, software engineering, or mathematics, or that's not necessarily what I'm interested in as an employer. Questions that employers are going to ask, or at least employers that I are going to focus on what we talked about. So they're going to talk about fundamentals of software engineering. They're going to want to understand, evaluate technology, and that you know how to work inside of a team. They want to know that you can communicate your thoughts. That's right. Thoughts and ideas. Well thought out. They're well defended ideas. They want to know that you put time into choices, and ramp up in their tech stack. So you can start contributing to the team. There's no way that any degree train expect that my team uses. Not possible. There's too many novel things and unique things with every single job. I'm interested that you know how to do it, not that you already know all the things I expect you to. So yeah, I would say regardless of what major you pick, make sure that it's something that you find it, not necessarily picking it. That's it. Thanks. I hope you found some of this useful. Do you want to do questions or no? Does anyone have questions? Okay, you first. I'm not gonna disagree with one of your props. I think it depends on the diagram. So the way that I would typically ramp up, say, they don't have to school. I'm gonna ramp up low complexity projects or work to start with. So something localized changes. So you're going to be working on a feature, and I happen to know that feature is in 6 files. Make that change, get used to the process of making a change, get used to the quality requirements that we expect, and then slowly introduce more and more complex. That's typically. Yeah. So that's a good question. A lot of it depends on you and your own. So what I've done is always make sure that during my workday, like I'm not doing this out of hours. I'm doing this. So typically what that looks like is whatever company I'm working for uses, what the developments are. I would say is the most useful. So I'm not interested in something theoretical. I'm not interested in chat. That is, yeah. So I'm not interested in taking Chat GPT tomorrow and starting to write all of our code with it. Maybe that's a thing that I should care about, but I don't. I'm more interested in developments closer to my own tech stack because I can apply them. So I would say that's how you stay connected. Oh, like literally what am I doing? Okay, so yes, so a great resource is letters. So if you, something that's very relevant to my role is identity. So how do we know that someone who logs in or something is who they say they are? That's a very, there are a whole bunch of organizations that publish that have website products. So like CrowdStrike is a vendor, and they publish letters that talk about. So I would say the most authoritative information that's typically the highest quality. It's not bad, but it's too broad, it's too vague, and I wouldn't consider that high quality. I don't know what. So I would say, answer your question first. What got me into the position I have now. I would say these things I did. But these are the things that I would say. How did I originally get into software? So when I graduated high school, I was debating between software engineering. Philosophy versus software was because I love philosophy. That worked out. And then between software and computer and the other one, I didn't like science. Kind of simplistic. So cloud what, sorry? Yeah. So it depends on the industry. So working at RBC, RBC is a bank. They have a lot of obviously older systems, right? They started adopting technology 50 years ago. So does anyone know what COBOL is? COBOL? That's roughly the ratio I would expect. So COBOL is a very old programming language. This was written 50 years ago. Core stuff. The way that you used to keep track of account balances, walk into a branch, you'd take money out, the teller would write down on a piece of paper. That was it. That was the whole process. Then they put that onto computers. They did it on computers one time and said, we'll never have to do this again. Those programs are running on mainframes. Those programs will probably never move to the cloud. Because there's no reason. They work well, they're time tested, they're bulletproof, leave them alone. But all of the other stuff, so think of like a banking app or a new banking iOS app. Like the back end for that could very easily be out. So in terms of the rate of industries moving to cloud platforms, I would say today, if you're starting a business, I have a hard time imagining but run on the cloud. Or legacy enterprises that have a lot of investment in they're going to move any ancillary operations by providers for cost, minimize cost and risk, and that core piece of business, banking, that's going to live in their own data centers for a long time. I wouldn't see that. Question? No. So I didn't do any. Not really. So Advent of code. Advent calendar. So I did that. So I do. Good question. So you're trying to get into one of those companies, you go on buy a book or whatever book you tell you. There's all kinds of books out there like Craft or whatever. That's fine. I think what I look for, not for I look for much more. So co-op terms. Co-op terms make a huge difference. And it doesn't matter necessarily the company that you at or what makes a difference is when I'm hiring someone as work experience, I know they know how to work in office. That's not like all of these are really important things that when you're in school aren't happening. You don't, I don't think, have a class on how to respond. But in your job, If you don't show up to meetings, it's very annoying. Very difficult. You have models and that's going to help me know that you've gone through some of that just general professional stuff. The other thing is that I would know you know about how to work against timelines, how to work with engineers. I know you have to stand up, learning and that is really important. I would say that's the most important stuff. Like I said before, it's very unlikely that you are going to be prepared for your job from a technology perspective, right? Because you don't know that you're going to be like, yes, it's probably Java. Probably, if you're working on anything back, it's probably Java today. But you don't know that, and even in Java, you're not going to know the ins and outs of the framework and the ins and outs of so it's much more important to show examples. That's the most important thing, especially for hiring. I don't know if you wrote the code. I would say very vague. You're all blank. It's fine, it's still a project. But if your commit messages are really detailed, it shows that you planned out. Thought about your changes as you were making them. So I look at commit logs. A lot of your probably I will stay in it. I enjoy the process. I enjoy that part. So I often the scale. So depending on very often sit down in front of a $1,000 program and are told to make this. Like, oh, where do I start? And then they make a change. They're like, how do I deploy this change? Like, where's the button to push? So the scale, deployment perspective, I would say that on their machine, a very local environment. Know everything about because they set it up. Thousands of engineers all work in a shared system all at once. And that volume. That said, every single person is always overwhelmed. So there's no expectation that you would not be. It would be crazy if you sat down and I was like, oh, okay, here's your 50,000 file program. I did it. I would be shocked. I would accuse you of it. Okay. So yeah, it's expected, but that's the most common structure. Cool. I think if you really wanted to prepare yourself for that, closest thing I can do is large open. So contributing to a large open source project is a similar scale. Actually, real. So if you're talking about like a portfolio, actually, if you have real commits, open source project like Kubernetes. If you have a commit on Kubernetes or a sequence of commits or a PR that's merged, that's great because that was audited. Somebody looked at that code. Google as a, so you're leaning on their reputation. So that would be one way to that's probably the best one because then you know it's real. Yes. Always. Yes. So the way it kind of breaks down is non-call switch. That's a good question. So I have my PNG. That was a personal goal for me, and I really do encourage you to get it. That said, it definitely doesn't matter. I don't like saying that out loud, but the simple reality is you don't look for it. I don't look for that you I guess certain systems. Projects. You get a co-op position. So like I said before, I don't like you mean to prepare for like the interviews. Yeah. It would depend. It just depends so much on where the co-op goes for, right? If you're building like front end project is probably the most important. If you're building out like back-end APIs, having a back-end project is probably more important. But I would say no matter what, show something that's complicated. That's the most important. If it's something that's complicated, then I know you can that's probably what I'm going to be giving you. So don't worry too much about the technology. Have the right buzzwords in it, or like is it that? Make sure that it has sufficient that the problems you're picking up are solved in an elegant way, and that's going to be very useful. I would say that. So I guess what I would say is, so it's not something I personally would look at as, what I mean by that is I wouldn't look at a resume that has like an identical resume, but one says like organizer of like the computer science club and one that doesn't. You're like, well, obviously we're going tennis club person. So that wouldn't happen. But what I would say is that doing extracurriculars are going to happen. So when people say like a well-rounded resume, less about the resume and like the line items, like you're not getting it for points. You're getting it for if you're an organizer of a student society, you're going to have to like like, get people in a room and convince people of the idea. You're going to practice some of the professional skills that you're going to need. So you'll do better in the interviews. So I would look at it more from that lens than like a list of extracurriculars that doesn't really happen. Stack Overflow. I don't not rely on Stack Overflow. So actually, the first month job, I was having a problem with got in trouble. Java framework. Hosted on Stack Overflow. So I actually was working with the student. Sent for thing I was having a problem with. Yeah. That it? So I copied and pasted it. When I talked to them today, showed me the Stack Overflow. Like, don't. Like, oh no. So I got called out. I don't. I would say do a lot. Like, there's internal. Very simple, obvious reason for that is copying and pasting source code. Anything else? Okay. So one and rest. Hypothetical is like have an employee or the inverse is you have an employee. Either way, they're not working anymore. So how do you handle that? Pretty common problem in management. The way to do that is to siloing. So I have a staff of say 10 engineers. I'm not going to have them all work on separate things entirely. I have 2 projects that 5 people are each working on. And you get a lot of knowledge sharing. You get a lot of like good things about working with others. Like it's just a better feeling than like closet coding all day. But to address what you're talking about specifically, everyone shares the knowledge of that project. So one individual leading to a better outcome. There's well established. I would say if my team should. Folks on my team. How to impress your manager? I mean, it's so dependent. I would say don't worry about impressing the manager. Like, at the end of the day, hopefully the manager sets requirements. Go well, explain to you what you're job well. Should be all those required. I wouldn't do it. Have to do that, then find a new manager. Any last questions? Okay. Thank you all. Yes. Blockchain. Okay. So blockchain. So I have colleagues who work in crypto for like Kraken and companies like that. Blockchain will not replace the banking system. The reason is that blockchain. Is anyone here a big fan of blockchain? Like loves blockchain? Yeah, a little bit. Okay. So here's my take on blockchain. It's a very expensive database. That's it. That's all it's doing, especially in a banking scenario. So if you imagine a private blockchain, a blockchain that doesn't need proof of work or anything like that because it's not public, not anyone can write to it. It's just a very expensive database. It's a ledger, sure, of records, okay, that I need to query and modify and so on. So there's no point. If I'm a bank and I have a lockdown database, it's as good as a blockchain, but way less expensive to run. So that's kind of it. I don't see banks throwing out databases. I've actually seen a drop of blockchain adoption across large companies like Merce, big shipping company. They were tracking parcels on blockchain. They had a partnership with, I think, IBM to do that, and they got rid of it. They had it when blockchain was really like a big deal. They raised a bunch of money for it, and then they discovered it was really, really hard to operationalize and really expensive. So they replaced it with the database. That's really all it was at the end of the day. So I think there's good blockchain applications, but I don't know what they are. Novel technology, no matter what. Okay. Thank you, everybody.
All right, thank you everyone. Feel free to take food. There's still like plenty of food.